There are two more things we need to talk about with the integrals of type 1 here. But one is, what happens if you're going from negative infinity to infinity instead of having one of those endpoints being a finite number? Well, what you do there is you take the integral and you break it into two pieces. The idea behind that is you're trying to find the area under some curve. Maybe it looks like a bell curve or something. If you're trying to find the area under that from minus infinity to infinity, you split it somewhere. And you find this area, and then you find this area, and you add them together. And it doesn't matter where that split point is. It can be anywhere on the real number line. So that's what's going on here. This is the area up to b. This is the area from b to positive infinity. And you just add those together. And b can be any number you want. 0 is a convenient thing to choose sometimes. Basically, you just want to choose something that's easy to plug in. All right, I also want to look at comparisons. I've got two integrals here, and I want to look at them individually. So how do you deal with something like this? Integral from 1 to infinity of 1 over e to the x dx. We haven't seen how to deal with that yet, but I want to look at it on Desmos. So I'm just going to put that function in. Y equals 1 over e to the x. Let me zoom out here. And let's restrict that to only going between x is between between 1 and infinity. So I don't have to put the other part on there. So we've got this. So the area under that curve, is it finite or infinite? Well, I don't know right off, but here's how we can figure it out. Let's graph something else. Let's do y equals 1 over x. I'm going to do that from 1 to infinity. All right. Well, what do we know about the area under the blue curve? Tell you what, I'm going to, if I change this from an equal to a less than or equal to, put that in there. If we look at that blue area is under the curve 1 over x. So the blue area is infinite. But unfortunately, that doesn't tell us anything about the area under the black line. The area under the black line, it could be infinite or it could be finite. But what if we compare, I'm going to change my blue curve and the area under it to x squared. Now, we already know that the area under 1 over x squared, we know that area is finite. And so the area under 1 over e to the x, it has to be finite as well. So that tells us by comparison that, that this integral is finite. It doesn't tell us what it is, but it does tell us that it converges, that it's finite. Let's see how to write that down. Okay, for this one, I could say since integral from 1 to infinity of 1 over x squared dx is finite, another word for that is convergent, and 1 over x squared is greater than 1 over e to the x for all x in the interval from 1 to infinity. All this is saying is, this is just saying that the graph is underneath the other one. That it then integral of 1 over e to the x from 1 to infinity is also finite. And as far as wording goes, we can either say that the area is finite, we could say that the integral is convergent, or we could say the interval converges. The integral converges. So any of those are fine. Now we can do something similar for this one over here, but I want to bring this one down and work on it separately. I stuck a new page in here to work on this thing. There are two things we could do. If we just wanted to answer whether or not this thing converges or diverges, then we could compare it to x squared. If you come over here and you look at x squared, let's look at Desmos. I've got 1 over x squared graphed in blue and the area underneath it. If we change this to 1 over x squared plus x, we can see that the area under the black curve here, it's less than the area under the blue curve. So just by looking at that, we can tell that it's going to converge. So let's come back over here and write that down. This converges because integral of 1 over x squared from 3 to infinity. Now, notice over there, I didn't look from 3 to infinity, I looked at 1 to infinity. But it doesn't really matter. If I change these things to 3's, it's just going to cut off part of the graph. And it doesn't matter if you cut off a finite bit. If the thing's infinite, the rest, if you've got an infinite area and you cut off a finite part of it, what's left is still infinite. So this thing converges because this converges. And 1 over x squared plus x is less than 1 over x squared. Why is it less? Because it's got a bigger denominator. It's less than that for all x in the interval from 3 to infinity. Why 3 to infinity? Because that's what we were asked about. Okay, could we figure out what this one equals? Yeah, absolutely. To compute this, what we have to do is use partial fractions. So 1 over x squared plus x, I'm going to factor that into x times x plus 1. It's a over x plus b over x plus 1. And as far as partial fraction problems go, this one's pretty tame because we can plug in x equals 0. I need to multiply this out. You get 1 equals a times x plus 1 plus b times x. So if you plug in x equals 0, you get 1 equals a. And if you plug in x equals -1, you get 1 equals negative b. So b is -1. So we can rewrite our integral as integral from 3 to infinity of 1 over x minus 1 over x plus 1. Now we just have to integrate this. This was actually pretty easy. You get ln of x. I'm going to leave my absolute values off of here because the numbers we're plugging in are just, they're all positive. So ln x minus ln of x plus 1 from 3 to infinity. Okay, if you plug in the infinity, let's don't plug the infinity in. Let's do this one. Actually, before we do that, let's use our log rules to put this together. You get ln of x over x plus 1 from 3 to infinity. And now we get ln of infinity over infinity minus ln of 3 over 4. You know what? I don't like doing this informally. Let's go back. Infinity over infinity, I want to call that 1, but it's not always 1. It is in this case, but I don't feel comfortable writing it out. That sets a poor example. So let's see, it's the limit as t goes to infinity of ln t over t plus 1, then minus ln of 3 over 4. All right, so what do we get? Well, this over here, sure enough, goes to 0. Wait, why does it do that? Because this goes to 1, and ln of 1 is 0, minus ln 3/4. How does it wind up being negative? Well, it's not really negative. 3/4 is 3/4 is less than e, so that logarithm is going to be 0. I'm sorry, it's going to be negative. If I put in ln of 3/4, my calculator, sure enough, it gives me a negative number. So I could write my answer as minus ln of 3/4, which is approximately 0.2877. And just for fun, let's look at what Desmos gives us if we graph that. So we're looking for it to be 0.2877. F of x is, what was our original function? 1 over x squared plus x. And we're supposed to take the integral of that from 3 to infinity. Now, you can't put an infinity into Desmos, so just put in a big number. So I'm going to put in 999 integral of f of x dx. And we were expecting this to be 0.2877. That's pretty close. And if I make this number bigger and bigger, it should get closer and closer to the actual number. And sure enough, it is. 0.2876 something, close enough. All right. So that'll do it for the type 1s. We'll look at, or before I go, the comparison stuff that we did here, we're going to do more of that stuff in chapter 11. So don't worry too much about that because it's not what I'm really going to focus on in this section. I just wanted to kind of foreshadow it because it's going to be important in chapter 11.